All right, so you've probably seen this thing making the rounds online. It's the so-called water-powered stove, and it looks like it completely bends the rules of physics. It's gone viral, and today we are going to get to the bottom of it. Is it magic, or is something else going on?
I mean, the claim is so simple and honestly pretty captivating. You take plain old water, you flip a switch, and boom, you get a flame you can cook with. It seriously feels like something straight out of a sci-fi movie.
And that really is the heart of the matter, isn't it? Is this some revolutionary breakthrough that's going to change our lives? Or is it more of a costly illusion, hiding behind a really cool-looking flame? Let's dig in and find out.
To really get this, we have to look past the simple question of, hey, does it work? Because, spoiler alert, it does. The flame is real. The real engineering question, the one that truly matters, is what does it actually cost in energy to make that flame?
So this right here totally reframes the conversation. We think it's water versus gas, but that's not the right way to look at it. See, both this hydrogen stove and a modern induction cooktop start with the exact same thing, electricity. One of them uses that power directly to heat a pan. The other one, well, it uses that power to create a fuel, which it then burns. It's literally just electricity with extra steps.
And those extra steps, they come at a steep price. Just look at these numbers. An induction stove is incredibly efficient. We're talking 90% of the electricity becomes heat in your pan. A regular gas stove, much, much lower, maybe 40%. And the hydrogen stove, well, it's pretty much the same as gas, hovering around 40% efficiency. That means you're throwing away more than half of the energy you started with just to get that flame.
So, to understand that huge energy loss, we've got to understand what hydrogen is actually doing in this system.
Okay, this is the most important point to get. Hydrogen is not an energy source, it's an energy carrier. Think of it like a battery. You have to pump energy into the battery to charge it before you can get any energy out. It's just a way to hold onto energy and move it around, not a way to make it out of thin air.
And here is where all that energy just vanishes. Every single step in this process is like a leak in the pipeline. First, you use electricity for electrolysis to split the water. Poof, some energy is lost as heat. Then you've got to compress and store that hydrogen. Poof, more energy is lost. And finally, when you actually burn the hydrogen, the fire itself isn't perfectly efficient. Each step just lets more and more of that initial energy escape.
Okay, but what about the water itself? That's a question I see all the time. Are we going to drain our rivers and lakes just to boil some water for pasta? It's a totally fair question.
Well, the reality is, not really. The whole process is actually pretty light on water use. We're talking about half a liter to maybe 1 liter of water for every kilowatt hour of energy you get. Now compare that to agriculture, which uses something like 70% of all our fresh water. The amount needed for this kind of cooking is just a tiny drop in the bucket.
So the next logical question is, okay, if we're worried about fresh water at all, why not just use the most abundant water on the planet, seawater? Can we just pump it right out of the ocean and into the stove?
If only it were that simple. Turns out the salt in seawater, specifically the chloride ions, totally wreaks havoc on the electrolysis. It messes with the chemistry and creates some really nasty, corrosive stuff like chlorine gas that would just chew up the equipment. So you'd have to desalinate the water first, which means, yep, you guessed it, even more processing steps and even worse efficiency.
Okay, so we've established it's not very efficient and you can't just use any old water. Now, this is normally the part of the story where we'd say, case closed, this is a bad idea, but that's not the whole picture. Not at all.
This is the million-dollar question that really unlocks the whole point of this technology. If it's so wasteful with electricity compared to a boring old induction cooktop, why would any sane engineer bother to build one?
Because it was never, ever meant to compete with the stove in your kitchen. This is a specialized tool. This is for resilience engineering. Think about places where you can't just get a propane tank delivered. We're talking remote villages, disaster zones after a flood, or maybe an off-grid cabin powered only by solar panels. In those scenarios, the rules of the game completely change.
And that's the exact problem it's built to solve. It's for when you have electricity, say from a solar panel, and you have water, but you have no fuel supply chains, no trucks, no pipelines, no gas stations. With this, you can create cooking fuel on site, whenever you need it. You get energy independence. It's not about being efficient. It's about being available when nothing else is.
So, when we pull all of this together, it gives us this fantastic lesson in how to look at any new technology. Not just with wide-eyed wonder, but with a bit of a critical engineering mindset.
This line from our source material really is the perfect no-nonsense summary. The magic of making a flame from water is, at the end of the day, just a roundabout and less efficient way of using the electricity you already had to begin with. It's a conversion, not a creation.
And this is the idea I really want to leave you with. For any new gadget or gizmo that seems like magic, the first question shouldn't be, does it work? The smarter question is, what problem does this actually solve? What is it replacing? And what is the true cost? Not just in money, but in energy, in materials, in complexity. Once you start asking that question, you start thinking like an engineer.